Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we want to explore the meaning of Constexpr, how it really works, and why it is more complicated than it looks. Constexpr static const. Any discussion about Constexpr, how it works, and where it can be used should also include where const will fit into the equation. We found the idea of having a Constexpr static const declaration an interesting idea and something worth investigating. What we did not realize at first was most of the information about Constexpr confuses a variable with a function and does not distinguish between what compilers do and what the C++ standard requires.
We traditionally like to start with a bit of terminology. It turns out both const and Constexpr are keywords, which we found a bit surprising. Initially, we did not think Constexpr would be a keyword, but rather an identifier. Keywords and identifiers are slightly different. An identifier can be the name of an object, a function, class method, or a variable. As of C++ 17, the only defined identifiers in the language are final and override. These two identifiers have a special meaning when used in a certain context. It would seem odd to name a method or a class override, but it is legal. The keyword const is part of the data type declaration. If const is being used in a variable declaration, the const establishes the initially assigned value can never be changed. The best way to think about const is as an agreement that some code will not change some data. It is essential to understand that unlike const, Constexpr is not part of the data type. Although it is a keyword, it acts more like a modifier or an adjective in a declaration. Keywords like static and inline are similar in nature to Constexpr. The order of the terms Constexpr, static, or inline in a declaration are not enforced. However, your code should be consistent in the ordering for readability. It is worth noting that you can write a declaration which says const Constexpr int or Constexpr const int, and the compiler will produce the same result. Since const is part of the data type, it applies to the data type of int. The Constexpr will be treated as a modifier of the entire declaration, even if the positioning makes it appear to alter the data type.
There are many different places that const can be applied to a data type. In these examples, the const always means X promises not to change Y. But for each one of these declarations, the X and the Y are different. In the third and fourth examples, the position of the const alters what cannot be changed. In example 3, the const indicates the pointer var a cannot be changed. In example 4, the const means the data var b points to cannot be changed. In these two examples, the placement of the const changes the meaning of the data type. In the last example, although it looks like const is applied to the method or maybe the return type, this is not true. The const here is called a const qualifier. There is a hidden this parameter which is inherently passed to a non-static method. A const qualifier tells the compiler that no part of this method will modify any data member in the class using the this pointer. Since Constexpr is not part of a data type, it can only appear once in a given declaration. These examples show where Constexpr can be used. The effect of adding Constexpr makes a request to the compiler to evaluate something at compile time. With some of these, the Constexpr also adds an implicit const which modifies the entire declaration.
The definition of a literal data type was added to support Constexpr variables and functions. The C++ standard states that only literal data types are allowed with Constexpr. So what is a literal data type? It is a data type which is guaranteed to be usable at compile time. There are several categories of literal data types, the first of which is called the scalar data types. Scalar types include the typical built-in types, such as integers and floating point numbers. All references are also considered literal data types. Surprisingly, void was not included in this list until C++ 14, which made Constexpr somewhat awkward to use in C++ 11. The most interesting category of literal data types are classes. Any user-defined class which meets specific requirements is considered a literal data type. Such a class must have a Constexpr constructor which can be used to create an instance of the class at compile time. It must also have a trivial destructor, which means the destructor is defaulted or not declared. Finally, all data members and base classes must also meet these same requirements. A Constexpr variable must be declared using a literal type. In a function marked as Constexpr, the return type must be a literal type, and each of the parameters must also be literal types. Only literal data types can be used in the body of a Constexpr function. It would be nice if the QString class in our CopperSpice library was a literal data type so it could be used in a Constexpr variable or function. So what would it take to change this class so it satisfies the requirements for a literal data type? These are the same questions you may need to ask about any class in the standard library, your own application, or even the Boost libraries. The first place we started was with the constructor. Typing the word Constexpr in front of a constructor is very easy, but you need to look a bit further at what the constructor is actually doing. To construct a QString, the storage for the string must also be constructed. Our string class uses std_vector for storage, and this container is not a literal data type as of C++ 17. Since the QString destructor will call the destructor for std_vector, our QString class destructor is not trivial. If we could specify a different internal storage to be used only at compile time, we could make our string class a literal data type. However, there is currently no mechanism to ask the compiler whether a function is being called at compile time or runtime. Adding Constexpr to a variable declaration has a specific meaning. The variable must be a literal type, and the value of the variable must be initialized at compile time. The data type of the variable is const, based on the definition of Constexpr. Constexpr requests the compiler to evaluate the given code at compile time. Under most circumstances, this will happen. However, there is no guarantee unless the evaluated value is used at compile time in another context. If you have a Constexpr variable and the value is not a literal type, you will get a compiler error. This is not proof that the compiler did the evaluation at compile time, but rather a notation that if it did, it would fail. It is important to stress that just because you have marked a declaration as Constexpr, there is actually no rule saying the compiler must evaluate the code at compile time.
The keyword Constexpr is sometimes thought of as an abbreviation for a constant expression. They do sound similar, but these are two separate things. Implying they are the same idea is not advised and is inaccurate. In the process of trying to define and explain these parts of the language, we discovered this talk was not simple and required a good deal of preparation. A constant expression is nothing more than a value which can be used as a compile time constant. A Constexpr variable adds the ability to save a compile time constant in a variable. A Constexpr variable declaration must be initialized with a constant expression. The declared variable becomes a compile time constant, which is usable in other constant expressions and in places which require a compile time constant, like array bounds, bit field sizes, and enum values. Our example shows two variables, both initialized with compile time constants. Neither of these variables is Constexpr, but they are both const. There has always been a rule dating back to C++ 98 that says any const integer variable, which is initialized with a constant expression, can be used as a compile-time constant. However, this rule only applies to integers and not other data types. Assigning the compile-time constant of 3.8 to the const variable var b is valid. However, it is not evaluated at compile time, since it is not an int. This means var b cannot be used as a compile time constant. In the first declaration, var a is a constant expression, even though it is not marked as Constexpr. The variables var a and var b can be used as compile time constants. The last two lines declare two other variables, var c and var d, which are initialized from var a and var b. This is a simple example, but it is extremely important to point out this code would not work if var b were declared with const instead of Constexpr. If we had used the keyword const in this declaration, var b would be const, but not a compile-time constant. Only integer data types are eligible to be expanded to a compile-time constant. Since we are about to use var b in the assignment of var d, we need the value of var b to be evaluated at compile time. If this feels a bit confusing, it is. This would be a good place to experiment with godbolt.org to test this code and see the compiler error you would get if var b were only marked as const. This code could not have been written prior to C++ 11 because there was no way to declare a variable of type double, which was a compile-time constant.
As we have already mentioned, Constexpr can have the side effect of adding const. This always happens when you use Constexpr to declare a variable. An implicit top-level const is added. This const might not be inserted in the same position as Constexpr appears. However, it will add a const to the data type in some location. Declaring a free function with Constexpr does not affect its signature in any way. In C++ 11, declaring a non-static method with Constexpr also added a const. The implicit const was a const qualifier, just as you would normally write at the end of the method declaration. So in C++ 11, if you had a Constexpr method, the implicit const meant you could not change the data members of the class. This was an oversight and subsequently removed in C++ 14. Here is another example where using Constexpr expands the const to a slightly different place than just using the const keyword would. When const appears at the beginning of the first pointer declaration, it declares ptre as a pointer to const int. This means the pointer can be modified to point to a different integer, but the pointer cannot be used to modify the value of the integer it points to. When Constexpr is used, as shown in the second declaration, it adds what is called a top-level const. This means that ptrf cannot be changed to point to a new location, but the data it points to can be modified. This is a subtle difference, but in terms of how pointers work, it is a rather huge difference. The initial definition of Constexpr in C++ 11 was very restrictive. The extreme limitations on Constexpr functions meant that most needed recursion to accomplish even basic functionality. This made writing Constexpr functions very tedious and limited. In C++ 14, a large number of the initial restrictions about what could appear in the body of a Constexpr function were removed. The other major change was the removal of the implicit const qualifier in a non-static method. If you were using non-static Constexpr methods, you need to review your code and ensure the const qualifier is present if required. In C++17, there were a few changes with Constexpr lambda functions, and a new construct called if Constexpr. This latter feature allows for conditional branching based on some compile time condition.
Although Constexpr and macros are different, they can sometimes be used to solve the same problem. However, there are fundamental differences. Constexpr variables and functions follow the normal rules of the language, like scoping. A pound-defined macro is a simple text substitution handled in the preprocessor. Sometimes the macro approach does not do what you expect. Whenever possible, a pound-defined macro should be replaced with a Constexpr declaration of a variable or function. Constexpr declarations are more readable, and your code will benefit from type checking at compile time. This moves the work from the preprocessor to the compiler, which provides better debugging with more descriptive error messages. Not all macros are candidates to be replaced by a Constexpr. The most common reason you will need to keep using a macro is that Constexpr values are not visible in the preprocessor. When a value needs to be tested in a poundif preprocessor directive, a Constexpr variable will not work.
In the code for myfunc1, there are two issues with the macro height1. Since the preprocessor does not understand scoping rules for C++, declaring a constant using a macro means you must undefine the macro if you want to reuse the term height1 or change the definition at some point. Keep in mind that height1 is not an identifier but simply a token. The substitution for the height1 macro with the value of 640 happens during preprocessing. In myfunc2, height2 is a proper variable of type int, and it is also an identifier. C++11 added the ability to declare a Constexpr variable, which makes height2 a compile time constant with a data type of const int. Since height2 is still a function local, it will go out of scope at the closing curly brace at the end of this function. Since 640 is an integer, using const in place of Constexpr would have been enough in this example to declare the variable as a compile time constant. If const had been used and the value had been based on a call to a function, the code would still compile and run. However, the variable height2 would not be a compile time constant. If you are using a variable as a compile time constant, you should always declare it with Constexpr. This will make your code clear about the intent and force a compile error if the value cannot be determined at compile time.
These declarations may look odd at first if you're not accustomed to using Constexpr. If you prefer, the keyword static can be moved in front of the Constexpr, as the order does not matter. We asked a group of compiler developers what order they would prefer, and no one had a reason for their preference. The order people picked was not based on anything specific. Constexpr was initially introduced in C++11, and this was just the beginning for compile time code evaluation. There were some mistakes and overlooked use cases. Later versions have cleaned up some of the problems and extended the language with things like Constexpr lambdas. It is speculated that C++20 will add new language features like Constexpr memory allocators, which will make existing structures and containers usable at compile time. It is good to know the Standard Committee is continuing to develop Constexpr to be more useful and of greater value.
For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.